So this is a video lesson on 10.2 and 10.3 in Chapter 10. It's going to talk mainly about arcs and chords with respect to circles. So let's go ahead and first lay out our first big vocabulary, which is arcs. And arcs is a key concept because there are different types of angles that can lie on or within a circle. Now, when I have an angle inside a circle, what that gets mapped to onto a circle is called an arc. An arc. So when I look at the angle, for example, AOB, and because that is a central angle, meaning its vertex is at the center, it's mapped to, the two radii mapped to the letters A and B, and therefore it forms the arc AB. The arc AB. Okay? And there's a special relationship that's held by the angles and their arcs, and that's based on the position of the vertex. And that's going to be a very important part here. We have to understand some just key terminology first. The first thing is a central angle. A central angle is an angle where its vertex is at the center, and the sides of that angle are represented by the sides are the radius, or the radii. The radii. Okay? So again, when we're looking at central angle, we're going to go ahead and use three letters to represent. It's going to be named with an angle symbol and three letters. So when I look at this picture, angle AOB represents a central angle where the vertex is at O, and that's at the center of the circle, and AO and OB are radii along that circle O. So then let's go ahead and look at minor arcs. Minor arcs. Minor arcs are part of circles that is less than 180 degrees. Sorry. Less than. That is less than 180 degrees. So when you think minor, you think of something smaller, right? Minor usually associated with something that's less significant or smaller. So again, part of a circle that's less than 180 degrees would represent a minor arc. We usually use this arc symbol, a curved line, over top of the letters that represent that arc, and we use two letters for a minor arc. And those two letters can be written in counterclockwise or counterclockwise directions around the circle. It just depends on what's the shortest distance from one letter to the next. So one example of a minor arc is the letters AB. AB represents a minor arc because its central angle is less than 180 degrees, and therefore the distance from A to B would be a minor arc along the circle. A major arc, where minor would be less significant, a major arc would be more significant. So here a major arc is a part of a circle that is more than 180 degrees. And we usually use three letters to denote a major arc. We use the arc symbol, and we're going to make sure that this arc that I travel along in my picture goes greater than 180 degrees, which is half a circle. So when I go from A to B to D and then all the way over to C, you can see how this arc would be something bigger than 180 degrees. Therefore, I need to pick three letters along that green arc to represent my major arc. So we'll start at A, because that's where my starting point is, clockwise. And then I can go to B, and then I end up at letter C. So then I'm going to draw my arc symbol, and that would represent an arc ABC. Okay? ABC. Finally, we have a semicircle. And a semicircle, again, if a minor arc is less than 100 degrees, a major arc is more than 180 degrees, then a semicircle is a part of a circle that is equal to 180 degrees. Again, we'll use three letters to represent a semicircle. And if I know for a fact that AD is the diameter of my circle. A diameter is a dead giveaway for which arc represents a semicircle, because the endpoints, or the letters A, B, D, the letters that I start and finish with in my arc, A and D, they have to be a diameter of the semicircle. That's part of the definition of what a semicircle is. So make sure that those letters match diameters to create a semicircle that is equal to 180 degrees. So based on the picture above, we can say that arc, because that symbol means arc AB is the intercepted, new vocab word, intercepted arc of the angle, central angle AOB. And if I have a central angle, its measure, the central angle's measure, is always going to be equal to its intercepted arc. Intercepted arc. The central angle is equal to the intercepted arc. And if you think about the word intercepted, intercepted kind of means kind of colliding into or connecting or touching. So make sure that the letters A and B are your starting and end points for your angle, A and B. So we're going to try one or two examples here together, and then you guys are going to be free to try some examples of your own and check them with the key. So here we're given a picture. It's important to understand that they told us that RT is the diameter of the circle. So that means it's going to cut my circle, P, into two congruent parts. This arc, RT, would be 180 degrees, and then this arc over here would also be 180 degrees. They tell me that the central angle RPS is 110 degrees, which means its intercepted arc would also be congruent of 110 degrees. The question is, what's the missing arc right here? Well, the missing arc that I can find would be supplementary to 110. So when I take 110 away from 180, I end up with 70, and that would be the central angle and the intercepted arc. So when they ask me to find the measure of arc RS, the measure of arc RS, I'm going to start at R, I'm going to go to S, and that arc is going to have a measure of 110 degrees. The measure of arc RTS, so I'm going to start at R, and let's use a different color pen here. I'm going to start at R, that's my starting point, and I'm going to go to T. The shortest distance to T and then S would mean that I would have to rotate counterclockwise, because I want to make sure that I go in the same direction to all three letters, from R to T to S. So R to T and then to S means that I'm going to add up 180 semicircle plus another 70, 80 plus 70, to find my answer. Now, Mr. Ausel, isn't this also the opposite of this 110? So couldn't I also do the full circle, 360, minus 110? Either of those expressions is going to give you the exact same answer of 250 degrees, and you could do it either way. Here I have the measure of arc RST, R to S to T. So I'm going to start here, I'm going to go the shortest distance to R, and then to T right there. Since R and T, those two letters, are my diameter, then I know that this is going to be a semicircle of 180 degrees. So, knowing we know about major, minor, and semicircles, major arcs and minor arcs, go ahead and try example 2. Check it with the key on the notes on the website, as well as go ahead and flip over to your own practice and try those problems as well. We're going to move forward at this point and kind of look at congruent circles versus congruent arcs. The important thing for congruent circles is that they have the exact same radii. They have congruent radii. And I just realized I misspelled radii on the previous page. Let me flip back here real quick. Let me add an extra I in here for radii. Alright. So, for two circles to be congruent, their radii, the distance from the center to the edge of the circle for both circles has to be the same. Now, if I look at a subpart or a part of a circle, which is an arc, if an arc is going to be congruent, two arcs are going to be congruent, I need to have the fact that circles are congruent, meaning I have congruent radii. And I also need to have central angles, congruent central angles. If I know the angles are congruent as well as the radii, then I know those arcs are congruent. So we're going to look at a couple examples, and you can try to complete the rest on your own. Here I have one circle, so obviously the circles are congruent to each other. They want to know if arc AB is congruent to arc CD. So since the segment BD or the chord BD passes through the center and the chord AC passes through the center, that would make the angles, the central angles, congruent to each other because they would be vertical angles because of the diameters. So since the central angles are congruent and I had the same circle, yes, AB would be congruent to CD. Example 2, we have two radii that are congruent with those tick marks. Also, the central angles are both 75. So yes, these would be two congruent two congruent circles or arcs. Here, I have central angles that are the same, but unfortunately, they don't tell me if the arcs are the same or the radii are the same length. Obviously, I can see that this circle is a little bit smaller than this circle, so I can't say for sure. But right now, based on what I'm given, these arcs would not be congruent. Here they want to know if AB is congruent to AB or CD. Now I know that the radii are the same, that's good, but I need to know if this angle is equal to 110. And the only way I can find that is by adding up the other two angles that I have and then going ahead and subtracting that from 360. And when I do that, I realize that the central angle, call this circle O, COD, is going to be equal to 110 degrees. So since the central angles are the same and the radii are the same, yes, this is a congruent circle. So if you flip to the top of your next page, which for me is at the bottom of this page, we're going to talk about the arc of two chords, and we're also going to talk about some theorems that exist between arcs and their chords. So the arc of a chord, which is at the top of your next page, is an arc where its endpoints, the endpoints of that arc, are the endpoints of a chord. Now, what is Mr. Ausel talking about here? If I have a circle, for example, in the theorem below, if I have a circle where arc AB goes from A to B, and the endpoints of that arc AB are the same as the endpoints of a chord AB, therefore that is a arc of the chord AB. Now, there's special relationships that occur here, and those are going to be our theorems in this class. The first theorem is that on the same circle, meaning congruent circles, two minor arcs, like AB and CD, are congruent if and only if, biconditionally, if and only if their corresponding chords, the endpoints of their arcs make chords, those chords are congruent. So, AB arc is congruent to arc CD if and only if AB, the chord, is congruent to CD, the chord. And everybody can see the difference between the two notations. This is an arc notation, and this is a chord notation. Alright, so let's go ahead and flip to the next page, or for you guys, do halfway down the page here. We have some practice problems to try. So let's go ahead and just briefly look at those. Here I have two congruent circles. I also know that the chords are the same length. So if the chords are the same length, that means their intercepted arcs, GF, would have to be congruent to JK. So if JK is 80 degrees, then the measure of arc GF or FG would also be 80 degrees. Here I'm given one circle, and that circle has two chords, AB and BC. Since AB has the same length as BC, that means that they're congruent. And if their chords are congruent, that means their arcs are going to be congruent. So that tells me that arc AB will be congruent to arc BC. In number 1, they tell me that AB is 110, meaning that the measure of arc BC is also 110. In number 2, they tell me that AC, this is a little bit more challenging, so follow along here closely. AC is 150 degrees. So that's 150. I need to find AB. I don't know what AB is, but I do know that AB is congruent to BC. So if a whole circle is 360, and I take away 150 from 360, I end up with 210. So this arc from A, B, C would be 210 degrees, because 210 plus 150 would add to 360. Since that's going to be bisected in two smaller arcs, I can go ahead and divide 210 in half, and I end up with 105. That would be the measure of arc AB. Alright, so we know that if two chords are congruent, then their arcs are congruent. The arcs of the chords are congruent. If one chord is a perpendicular bisector, those are two words that we've heard before, perpendicular bisector. Just as a quick recap, perpendicular means that they form a right angle, and bisector means it's bisected or cut into two congruent parts of another chord. So if one chord is a perpendicular bisector of another chord, the first chord that was perpendicular and it bisected the other segment has to be a diameter. Has to be a diameter. So if I know in my picture here, and this is a letter T, if I know in my picture that SP is perpendicular to TH, or TR I should say. If I know that SP or SQ, I guess I'm going to go all the way through. Let's erase that, make this SQ. If SQ is perpendicular to TR and TP, if TR is bisected, that TP is congruent to PR, then I know that SQ must be a diameter. SQ must be a diameter. With that same theorem being true, I can also flip it on its head and say, if I have a diameter of a circle, I know it has to be a perpendicular to a chord, and then it bisects that chord. Also, since it bisects its chord, it also bisects its arcs as well, meaning that the two independent arcs would be congruent to each other, formed between the diameter and the chord. So let's kind of just use some example problems of this just to make sure we understand it. So here we have a diagram of circle E. We know that AC is a chord. They want us to find the length of A to C. So since BD is a diameter because it goes through E, and they tell me it's perpendicular, then I know it's a perpendicular bisector. So if FA is equal to 7, then I also know that CF is also equal to 7. And if I'm asked to find the length of AC, I'll just put those together and I'll get a length of 14. Here I can see that BD is a diameter of circle A. Also, they tell me it's perpendicular to this chord. So since it's perpendicular, it's going to bisect the chord, but it's also going to bisect the arcs. So meaning that ED would be congruent to CD. Arc ED is going to be congruent to arc CD. that'll be really helpful because I know their arc measures with respect to x, so all I need to do is set 9x equal to 80 minus x and solve for x. When I do that, I get x is equal to 8, and therefore the arc CD would be 9 times 8, it would be 72 degrees. DE would also be 72 because it's bisected, and therefore CE, the combination of the two, would be their sum, 144 degrees. You guys have been doing a really good job paying attention at home and watching the video. We got one more theorem to cover, and then that's it for this video lesson. So, good job and keep up the good work. Here we have a theorem where we're given the same circle or two congruent circles. Two chords are formed along that circle, CD and AB in our diagram. And those chords are congruent to each other if and only if they are equidistant from the center. Equidistant from the center. Now, equidistant means that the shortest distance between any two lines to a point is always going to be a perpendicular length. So, just as a quick recap to write this down in your notes here below, the shortest distance is always perpendicular to a point. So again, if I'm trying to find the distance from C to D to E, I'm going to find the perpendicular distance to that point. So here, we're given a picture where a lot of information is already given to me. I know that this distance is 2x, and it's perpendicular to the chord QR. And this distance, CV, which is 5x minus 9, is perpendicular to the other chord. So since I know that QR is congruent to ST, that means their distances from the center are also going to be congruent to each other. So then I can set up 2x is equal to 5x minus 9, and when I solve for x, I end up with a x equals 3. Now that's not what I was asked to find. I was asked to find the length of C to U. So I'm going to go ahead and look at CU, which would be equal to 2x, and I'm going to plug in 2 times 3, which would have a length of 6. CU would equal 6. So that's the end of our lesson on 10.2 and 10.3 on arcs and chords. Make sure you practice these theorems and apply them to problems to better understand their relationships. Thanks.